One problem with Gaussian elimination is that we almost always encounter fractions. So let's start out with this system of equations, which is already written in standard form, which means we can put down our augmented coefficient matrix almost immediately. Now our first row pivot is 2, so we need to multiply that first row by 1/2 to make that pivot equal to 1. And so we'll multiply each term in that first row by 1/2. 2 times 1/2 is 1. 3 times 1/2 is 3/2. 1 times 1/2 is 1/2. And 6 times 1/2 is 3. We no longer need the original first row, and the other two rows remain unchanged. Next, if we multiply this first row by -3 and add it to the second row, that will eliminate the entry below the first row pivot. So we'll keep our first row, and we'll multiply each term by -3. So 1 times -3 is -3. 3/2 times -3 is -9/2. 1/2 times -3 is -3/2. And 3 times -3 is -9. Now we'll add this row to the second row, and we'll copy down that second row closer for convenience. So -3 plus 3 is 0. -9/2 plus 0 is -9/2. -3/2 plus 2 is 1/2. And -9 plus 5 is -4. Now we can also record this as -3r1 plus r2 replaces r2. And we'll keep the original first row, the new second row, and the original third row. And the other rows are unnecessary, so we don't have to keep track of them anymore. Now we'll want to eliminate the leading entry in the third row. So if we multiply the first row by -5 and add it to the last row, we'll get a 0 there. So -5 times 1 gives us -5. -5 times 3/2 gives us -15/2. -5 times 1/2 gives us -5/2. And -5 times 3 gives us -15. We'll copy down the original third row closer for convenience, and we'll add -5 plus 5 is 0, -15/2 plus 2 is -11/2, -5/2 minus 1 is -7/2, and -15 plus 6 is -9. So our new coefficient matrix is going to include the original first row, which we didn't change, the second row, which we also left unchanged, and our new third row. And we'll go ahead and copy down our new augmented coefficient matrix for reference. So our first row, 1, 3/2, 1/2, 3. Our second row, 0, -9/2, 1/2, -4. And our third row, 0, -11/2, -7/2, -9. Now we'll continue the Gaussian elimination by moving on to the second row. Since the leading coefficient in the second row is -9/2, we'll multiply everything in that second row by -2/9 to make that leading coefficient equal to 1. So our first row we'll leave unchanged, and our second row we'll copy down close by for reference. 0 times -2/9 is still 0. -2/9 times -9/2 is 1. -2/9 times 1/2 is -1/9, and -2/9 times -4 is 8/9. And the result will be our new second row, so we can erase the old row. And since we haven't done anything with our third row, we'll copy that over, unchanged. Next, since the leading entry in our third row is -11/2, if we multiply our new second row by 11/2 and add it to the third row, we'll eliminate that leading entry. So the first row will be unchanged. The second row will be our new second row. We'll multiply that by 11/2 to get 0, 11/2, -11/18, and 88/18. Adding this to our third row, 0 plus 0 is 0. 11/2 plus -11/2 is 0. -11/18 minus 7/2 is -74/18. 88/18 minus 9 is -74/18. Finally, we'll make the leading coefficient in the third row equal to 1 by multiplying it by -18/74. So multiplying that third row by -18/74 is going to make it 0, 0, 1, 1. And this gives us our final row reduced form. Our first row, 1, 3 halves, 1 half, 3. Our second row, 0, 1, negative 1 ninths, 8 ninths. And our third row, 0, 0, 1, 1. And now that we're in row echelon form, we can solve the system through back substitution. So our last row corresponds to the equation z equals 1. Our next to last row corresponds to the equation y minus 1 ninth z equals 8 ninths. And the first row corresponds to the equation x plus 3 halves y plus 1 half z is equal to 3. And now we can try solving our system of equations through back substitution. Starting with the last equation, z equals 1, we'll solve that for z. There it is. Our next to last equation, y minus 1 ninth z equals 8 ninths, we'll solve that for y, substitute in our value of z, and find that y is equal to 1. And our first equation, we'll solve that for x, substitute in y and z, and solve for x. And this gives us our solution, x equals 1, y equals 1, z equals 1, or as a vector, 1, 1, 1. And we notice that even though our system of equations has coefficients and constants all equal to integers, and our solutions are also all equal to integers, the process of Gaussian elimination produced a lot of fractions along the way. Now, less than 5/4 of the population have problems with fractions. So if you like working with fractions, then classic Gaussian elimination is perfectly feasible. And in fact, we can't avoid fractions forever, because sooner or later we'll run into a problem whose solutions are fractions or decimals. However, there are some ways that we can delay using fractions for as long as possible, so we'll take a look at that next.